Welcome to today's session. We'll be exploring LeetCode problem number 2180, count integers with even digit sum. This problem challenges us to determine how many integers, less than or equal to a given number, have an even digit sum. It's a great opportunity to practice basic number manipulation and algorithm design. Let's dive in. The problem asks us to determine how many positive integers, up to a given number, have a sum of their digits that is even. For example, if the input number is 4, we need to evaluate all integers from 1 to 4 and check whether their digit sums are even. The input will always be a positive integer within the range of 1 to 10,000, and the output should be a single integer representing the count of numbers that meet the condition. The task is to devise a method to compute this efficiently, ensuring our solution works even for the largest possible value of number within the constraints. To clarify this with an example, consider the case where number is equal to 4. The integers from 1 to 4 are 1, 2, 3, 4. We calculate the sum of the digits for each number. For 1, the sum is 1, which is odd. For 2, the sum is 2, which is even. For 3, the sum is 3, which is odd. And for 4, the sum is 4, which is even. Out of these, the numbers 2 and 4 have even digit sums, so the output is 2. This demonstrates the process of checking each number up to number and determining whether its digit sum is even. Now, let's look at another example where number is 30. Here, we evaluate all integers from 1 to 30 and count those with even digit sums. The numbers with even digit sums in this range are 2, 4, 6, 8, 11, 13, 15, 17, 20, 22, 24, 26, 28, and 30. In total, there are 14 such numbers. Therefore, the output in this case is 14. On the other hand, for smaller inputs like number equal to 1, the only number to consider is 1 itself, which has a digit sum of 1, an odd number. As a result, the output is 0 since there are no integers with even digit sums. To summarize the constraints, the value of number will always fall between 1 and 10,000. This means we need to ensure our solution is efficient enough to handle even the largest input size. For edge cases, when number is 1, the result is straightforward since there are no integers with even digit sums. When number is a single-digit number, only the even numbers in that range contribute to the count. For larger inputs, the solution needs to handle mixed digit sums effectively without unnecessary computation. Importantly, the algorithm must be optimized to avoid exceeding time limits for the upper boundary of the input range. To tackle the problem of counting integers with an even digit sum, we considered multiple approaches. The most straightforward method is the brute force approach. Here, the idea is simple: iterate through every integer from 1 to the given number, calculate the sum of its digits, and check if the sum is even. If it is, we increment a counter. This approach relies on breaking down each number into its individual digits using modulo and division operations. Once we have the sum of the digits, we perform a quick check to see if it's even, and if so, we include it in our count. Finally, we return the total count of valid numbers. This method is intuitive and easy to implement, making it a good starting point for solving the problem. Analyzing the brute force approach, we see that its time complexity is n*d, where n is the input number and d is the average number of digits in the numbers we process. Since d is proportional to the logarithm of the number, this can be approximated as n*log number. The space complexity is 1, because we don't use any additional data structures. While this approach is simple and straightforward, it's not the most efficient for larger values of number, such as those close to 10,000, because we are individually processing every number. To address this, we also explored an optimized approach leveraging mathematical observations. By focusing on the behavior of digits and their contributions to the sum, we can potentially pre-compute results or skip unnecessary checks. However, the constraints of this problem make the brute force method sufficiently efficient, so these optimizations are not strictly necessary. For cases with larger constraints, an alternative approach like digit dynamic programming, or digit DP, could be valuable. This method involves calculating the count of valid numbers based on their digit sums up to the given number, allowing us to build a solution more efficiently for massive input sizes. However, in the context of this problem, where the upper limit of number is 10,000, digit DP introduces unnecessary complexity. Given these constraints, we chose the brute force approach. It strikes a balance between simplicity and efficiency, running in n asterisk log number time, which is more than sufficient for the problem's input size. One key insight is that we only need to focus on the sum of digits, we don't need to store or process the numbers themselves beyond that. This observation simplifies the problem and ensures our solution is both clean and performant. Our decision to use the brute force approach over alternatives is based on its minimal implementation complexity and efficiency for the input size. While an optimized mathematical approach might offer marginal performance improvements, it also introduces additional complexity that is not warranted for this problem. Similarly, digit DP is a powerful technique for larger constraints, but it's overkill here given the constraints of the problem. In conclusion, the brute force approach is the ideal choice for this scenario. It is easy to understand, simple to code, and performs well within the given limits. By focusing on the properties of digit sums and leveraging the problem's constraints, we achieve a solution that balances readability, efficiency, and simplicity without overcomplicating the implementation. To solve this problem, we need to count how many integers from 1 up to a given number have a digit sum that is even. For instance, if number is 30, we need to identify how many numbers between 1 and 30 meet this condition. To break this down, let's start by understanding the concept of a digit sum. The digit sum of a number is simply the sum of all its individual digits. For example, the digit sum of 23 is 2 plus 3, which equals 5. A number has an even digit sum if the result of this addition, when divided by 2, has no remainder. Mathematically, this is expressed as digit underscore sum percent 2 equals 0. With this understanding, we can use a brute force approach to solve the problem by iterating through all integers from 1 up to number, calculating the digit sum for each number, and checking if it is even. If it is, we increment a counter. At the end of the loop, the counter will represent the total count of numbers with even digit sums. This simple approach lays the groundwork for more efficient solutions. Now, while the brute force method is straightforward, it becomes inefficient as number grows larger because calculating the digit sum for each number repeatedly is computationally expensive. To optimize this, we can take advantage of the predictable way digit sums change as numbers increase. For example, when moving from 29 to 30, the digit sum changes because the 10's digit increases by 1 and the 1's digit resets from 9 to 0. By observing these patterns, we can calculate the digit sum incrementally, rather than recomputing it from scratch for each number. In this optimized approach, we start by initializing a counter to track the count of numbers with even digit sums and a variable to keep track of the current digit sum. As we iterate through numbers from 1 to number, we update the digit sum based on how the digits of the number change. Once the digit sum is updated, we check if it is even and, if so, increment our counter. At the end of the loop, the counter will hold the desired result. This optimization reduces redundant calculations, making the algorithm more efficient. To understand why this optimization works, let's delve into the mechanics of digit sum calculations. Typically, the digit sum of a number is computed by repeatedly extracting its digits, which takes O log x time for a number x. However, for consecutive numbers, we can leverage modular arithmetic to update the digit sum instead of recalculating it entirely. This eliminates unnecessary work, especially for numbers with many digits. Checking if a digit sum is even is also very efficient. It's a simple parity check, where we take the digit sum modulo 2. Additionally, the observation that digit changes follow predictable patterns allows us to make incremental updates to the digit sum, rather than starting from scratch for each number. This approach not only reduces the time complexity but also keeps space usage minimal. We only need two variables, one to track the count of numbers with even digit sums and another to maintain the current digit sum. This ensures the algorithm is both space efficient and fast. By avoiding redundant recalculations, the optimized approach significantly improves upon the brute force method. The optimized approach also ensures the algorithm handles edge cases effectively. For small values of number, such as 1, the logic should correctly account for the single number. Similarly, the algorithm must handle sequences of numbers with consecutive even or odd digit sums without errors. For large values of number, up to 10 to the power of 4, the efficiency of the incremental updates ensures that the solution remains computationally feasible. To summarize, the brute force method has a time complexity of O n asterisk log n, as we process n numbers and compute the digit sum for each in O log n time. On the other hand, the optimized approach reduces the time complexity to O n, as updating the digit sum incrementally for each number is constant time. Both approaches have a space complexity of O1, as they use only a few variables. Here's a pseudocode implementation for the optimized solution. The function initializes a counter and iterates through all numbers from 1 to number. For each number, it calculates the digit sum and checks if it is even. If it is, the counter is increment. This simple yet efficient method ensures the problem is solved accurately while minimizing computational overhead. This implementation solves LeetCode problem number 2180, count integers with even digit sum, by iterating through numbers from 1 to the given input number and checking whether each number's digit sum is even. Here's a step-by-step breakdown of the code. 1. Helper function digit underscore sum underscore is underscore even asterisk. This function calculates the sum of the digits of a number and determines if the sum is even. We use a while loop to repeatedly extract the last digit, using x%10, and add it to total, then remove the last digit, using integer division x // equals 10. After processing all digits, we check if total %2 equals 0 to determine if the sum is even. 2. Main function count even asterisk. We initialize count to 0, which will track how many numbers satisfy the condition. We iterate through all integers from 1 to number, inclusive. For each integer I, we call the helper function digit underscore sum underscore is underscore even. If it returns true, we increment the count. 3. Return the result asterisk. After completing the loop, count contains the total number of integers with an even digit sum, which is returned as the final result. ### complexity. The time complexity is O n asterisk d, where n is the input number and d is the average number of digits per number. This is because we iterate from 1 to number, and for each number, we process its digits. The space complexity is O1, as we use only a constant amount of extra space. This implementation is efficient and handles all edge cases, including small inputs like number equals 1 and larger inputs like number equals 10⁻4. This is the Java implementation of LeetCode problem number 2180, count integers with even digit sum. The logic mirrors the Python implementation, using a helper method to determine if the sum of the digits of an integer is even. The main method iterates through all integers from 1 to the input number, applying the helper method and counting those with even digit sums. Key differences include explicit type declarations, the class structure required in Java, and the use of primitive types for efficiency. To solve this problem, we need to count all integers from 1 to a given number, where the sum of the digits of each number is even. The approach involves iterating through each number in the range, calculating its digit sum, and checking if that sum is even. If it is, we increment a counter that keeps track of these qualifying numbers. The final value of this counter will be our answer. For example, if number is 10, we start by initializing our variables. The variable count is set to 0, and this will store the count of numbers with even digit sums. Next, we iterate through all numbers from 1 to 10. For each number, we determine its digit sum using a helper function, digit underscore sum underscore is underscore even. For instance, when I is 1, we calculate the digit sum by adding its digits, which gives a total of 1. Since 1 is odd, the counter remains unchanged. Similarly, for I equals 2, the digit sum is 2, which is even, so we increment count to 1. This process continues for all numbers up to 10, incrementing the counter for numbers with even digit sums. In this example with number equals 10, the numbers that have even digit sums are 2, 4, 6, 8, and 10. This means the final value of count is 5. Now, let's look at another example where number is 15. Once again, we initialize number equals 15 and set count equals 0. We then iterate through all numbers from 1 to 15, applying the same logic described earlier. For each number, we calculate the sum of its digits and check if the sum is even. If it is, we increment our count. For example, when I is 11, the first digit is added to the second digit, resulting in a total of 2. Since 2 is even, we increment count. Repeating this process for all numbers, we find that the numbers with even digit sums are 2, 4, 6, 8, 10, 12, and 14. This gives us a final count of 7. By following this systematic approach, we can accurately count the qualifying numbers. Finally, let's consider a larger example where number is 20. We initialize number equals 20 and count equals 0, and then iterate through all numbers from 1 to 20. Using the same logic as before, we calculate the digit sum for each number and check if it is even. For this range, the numbers with even digit sums are 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. This gives us a final count of 10. Now, let's summarize some key observations. The helper function digit underscore sum underscore is underscore even efficiently calculates the digit sum of a number using modulo and integer division operations. The loop systematically processes each number in the range, ensuring accuracy. The condition total %2 equals 0 serves as the key check to determine whether a number contributes to the count. While this approach is straightforward, the time complexity is O, n*d, where n is the input number and d is the average number of digits per number. This makes the solution efficient for the problem's constraints. To analyze the time complexity of this solution, we begin by considering its main components. The count-even function iterates through all the integers from 1 to number, which means the loop runs number times. This gives us a contribution of O, number, simply from iterating over the numbers. Next, we look at the helper function digit underscore sum underscore is underscore even, which calculates the sum of the digits for a given number x. The number of digits in x is proportional to log 10, x, and in the worst case, when x equals number, this is approximately log 10, number. Therefore, the time complexity of the helper function is O, log 10, x. Since this function is called for each of the number integers, the overall contribution from the helper function becomes the sum of the digit processing times, which is roughly O, number asterisk log 10, number. Combining both components, the main loop and the helper function, the overall time complexity of the solution is derived as O, number asterisk log 10, number. Now, let's turn our attention to the space complexity of the solution. The space usage is determined by the memory allocated for variables and function calls. Starting with the helper function digit underscore sum underscore is underscore even, it uses a constant amount of space, O1, for storing the variables total and x. It does not rely on any additional data structures, and the digit sum calculation happens in place. Similarly, in the main function, only the variables count and I are used, which also require constant space, or O1. No memory usage scales with the size of the input number. Therefore, the overall space complexity of the solution is O1, indicating a very efficient use of memory. Finally, let's compare this implementation with a brute force approach and analyze its behavior in different cases. A naive brute force method would involve iterating through all integers from 1 to number, explicitly summing their digits, and checking if the sum is even. Essentially, this is what the provided solution does, but with an efficient implementation using the helper function to streamline digit sum calculation. No advanced optimizations or mathematical shortcuts are employed beyond this. In terms of best, average, and worst cases, the time complexity remains consistent at O, number asterisk log 10, number, because every number from 1 to number is processed without skipping. This uniformity means that the performance does not vary based on the input. To verify the complexity mathematically, we note that the main loop runs number times, contributing O, number, and the helper function processes a number with d digits in O, d, time, where d is proportional to log 10, number. Combining these, the total complexity is confirmed to be O, number asterisk log 10, number. Additionally, since the solution uses no input-dependent memory, the space complexity is constant at O1. Overall, this approach efficiently balances time and space requirements for the problem. When solving this problem, there are several common mistakes to watch out for. First, mishandling numbers with leading zeros can cause issues. While the problem only deals with positive integers, remember that a number like 00123 is mathematically equivalent to 123. Overlooking this can lead to incorrect digit sums. Next, you must reset the digit sum variable during iteration. If you're calculating the sum of digits for multiple numbers, forgetting to reset the sum for each new number will lead to cumulative errors. Another frequent misunderstanding is assuming the number itself must be even, but the problem is specifically about the sum of its digits being even. This confusion can result in valid numbers being incorrectly filtered out. Inefficiency is another issue. Using a brute force approach and recalculating digit sums from scratch for every number can be slow, especially for larger values of number. Finally, edge cases like number equals 1 or number equals 0 require careful handling. For example, number equals 0 has a digit sum of 0, which is even, so overlooking this can cause off-by-one errors in your results. Now, let's consider some key insights that are particularly useful in an interview setting. Recognizing patterns in digit sums can be a game changer. For instance, adding 1 to a number only affects the digit sum if there's a carry, and understanding such patterns can lead to significant optimizations. Additionally, precomputations, like prefix sums or modular arithmetic, can simplify the logic and reduce runtime complexity. It's also critical to stay aware of constraints and edge cases. For example, if the value of number is close to 10,000, a brute force solution might become impractical, and optimization techniques would be necessary. This problem also provides a great opportunity to apply modulus and digit manipulation concepts, which are frequently encountered in number theory problems. If you want to practice related concepts, you can explore problems like LeetCode 258, which focuses on reducing a number to a single-digit sum, or LeetCode 989, which involves digit manipulation in the context of adding an integer to its array form. Other related challenges include LeetCode 400, which deals with extracting specific digits, and LeetCode 7, which emphasizes edge cases in digit-level operations. Finally, let's explore alternative approaches and their trade-offs. A straightforward brute force method involves iterating through all numbers from one to number and calculating the sum of their digits. While this approach is simple to implement, it becomes inefficient as the input size grows. A more optimized approach leverages mathematical patterns in digit sums and modular arithmetic to avoid unnecessary calculations. Though it requires a deeper understanding of number properties, it significantly improves runtime complexity. Another option is to use precomputation, such as building prefix sums of digit sums, allowing you to quickly answer queries. However, this approach trades off memory usage for faster query times, which might not always be suitable depending on the problem constraints. By combining these techniques and tailoring them to the given constraints, you can turn this problem into an excellent exercise in mathematical reasoning and algorithmic design. Great work today! We reviewed count integers with even digit sum and covered key techniques to approach the problem. Remember to practice regularly and focus on optimizing your solutions. Thanks for joining, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!